Hello everyone, I'm Moitrey Dash and today I'm going to present our paper on a novel secret sharing approach for privacy preserving authenticated disease risk queries in genomic databases. Genomic data has become popular for early diagnosis of diseases. For example, people having family history of cancer, leukemia, heart disease, or diabetes may want to measure the risk of inheriting these diseases in advance so that proper diet and preventive treatment can be adopted. In this paper, we focused on processing a disease risk query, that is, computing the probability of an individual to develop a specific disease based on their genomic and clinical data. Now, why do we need to preserve genomic privacy? Because genomic data may reveal sensitive information regarding an individual's ethnicity, ancestry, traits, and health conditions. In addition, it can also reveal sensitive information about close relatives because genomic data is hereditary in nature. Such revelation of sensitive information may initiate discrimination in case of insurance, employment, etc. Besides privacy, we also need to provide authentication because processing disease risk query involves outside entities like a distress center, medical center, etc. These outside entities may change values of the genomic and clinical data used in the query. As a result, the computed disease risk may be incorrect. On the other hand, authentication ensures validity of genomic and clinical data used in the query and thus ensures correctness of computed disease risk. Now we need to review some genomic background information to understand how we can calculate disease risk from genomic and clinical data. Our DNA consists of two complementary polymer chains of 4 nucleotides. Those are adenine, cytosine, guanine, and thymine. These 4 nucleotides are represented as A, C, G, and T. If a nucleotide at a single position in a DNA sequence differs among the two DNA chains of an individual or different individuals, this variation is called a single nucleotide polymorphism or SNP. Each SNP carries 2 alleles, that means 2 nucleotides, one at each polymer chain of the DNA. For each of the 2 alleles, an SNP generally has only 2 probable nucleotides among A, C, G, and T. For example, SNP RS6311 in this figure has only 2 variations C and T. It does not normally have A or G. Both of these alleles of an SNP can increase risks for 2 or more different diseases. For example, C allele in SNP RS6311 can increase risk for rheumatoid arthritis, while T allele can increase risk for depression. If we want to calculate the risk for rheumatoid arthritis, then C will be the risk allele and number of risk alleles of these 3 patients having TT, TC, and CC in their DNA sequence will be 0, 1, and 2 respectively. We can compute the disease risk using this equation where we are aggregating the number of risk alleles Fi of each SNP multiplied with corresponding contribution factor beta I and the value Vi of clinical data multiplied with corresponding contribution factor beta bar I to generate the total disease score Z. Using Z, we can calculate PR, which denotes the probability of developing a particular disease. Researchers have considered several approaches for privacy preserving in disease risk queries. However, these approaches have limitations. For example, obfuscating genomic data may generate inaccurate disease risk query result. Again, anonymization also cannot guarantee privacy as SNP itself can be the identifier of the person. Researchers have also explored several cryptographic techniques, but these techniques also have limitations. For example, cryptographic approaches incur high storage and communication overhead. They do not consider both alleles of an SNP as potential risk alleles. Also, they cannot ensure genomic privacy if data storage and medical center collude. Compared to these prior approaches, we developed a secret sharing technique for both privacy preserving and authentication of disease risk queries that eliminates the limitations of other approaches. Our system mainly has 4 important components. Firstly, the Sequencing Institute SI performs the sequencing of genomic data. The SI may be directed by the government or any other trusted party. Next, we have N distributed databases or DDBs that are run by separate authorities such as private companies, cloud storage services, or non-profit organizations. The nth DDB is stored in the patient's personal device. At this point, one can argue that the SNP contents could be stored as a whole in the patient's device instead of N separate DDBs. However, patient's device can easily be hacked or stolen, leaving the genomic data in risk. In our system, we ensure that even if the patient's device is hacked, genomic data will be secured. unless other n-2 DDBs are also compromised. We also have a medical unit MU that processes the disease risk query. In case of disease risk query, we have to deal with two types of sensitive information. Some of them belong to the patient and other to the medical unit. Our privacy assumptions are dependent on the particular sensitive information. For example, genomic and clinical data are secret of the patient and it should be kept private from all other entities like MU, DDBs and eavesdroppers. Then name of the disease and disease risk query result are possibly known to MU, but these should remain private from DDBs and eavesdroppers. Medical unit which processes the query also have some secret information like contribution factors of genomic data beta I and contribution factors of clinical data beta I bar, which should be hidden from the patient, DDBs and eavesdroppers. Our basic system architecture looks like this, which I am going to explain in detail in the following slides. Basically, the patient gives his sample like hair or saliva to the SI. SI extracts SNPs from the raw genomic data and stores the value in n-1 DDBs using pseudonym for the patient. The SI also sends the remaining part to the nth DDB at the patient's device. It also generates an authenticating constant mu, which it sends to the patient's device. When a patient starts the query to know the probability of developing a disease, the MU sends a query message with necessary SNPs, risk alleles, and contribution factors to n-1 DDBs. The MU scales the contribution factors to hide them from the adversaries. It also includes information of dummy diseases along with the target disease to hide the name of the disease. Each DDB calculates partial genetic and authenticating scores using the data stored in there and sends back to the MU. MU then aggregates all those genetic and authenticating scores and sends to the nth DDB along with necessary SNPs, risk alleles, clinical data, and contribution factors. The nth DDB first authenticates to check whether the data it received from the MU are valid or not. If the authentication is successful, it calculates the total genetic and clinical score. For saving genomic and clinical data from potential malicious MU, it also changes the scores by multiplication and addition operations before sending them back to the MU. The MU reverses the effect of scaling contribution factors that it did earlier and sends the score for the target disease back to the nth DDB. Finally, the nth DDB reverses the effects of prior multiplication and addition operations to generate the final disease risk. Now I am going to explain how genomic data are stored in n-distributed DDBs. We use naive bit representation where each nucleotide is represented by 2 bits. A is 00, C 01, G 10 and T is denoted by 11. In this representation, if a patient has CT in a particular SNP, then the first allele is 01 and second allele is 11. Continuing the previous example, this table shows an example of how both alleles of SNP S1 can be stored in 5 DDBs, where 5th DDB is the patient's device. I will explain how the first allele of S1 is stored. Second allele follows the same procedure. For example, let's say patient has C in her first allele. So 01 is the real nucleotide of the first allele and the other possible variation is T. And that means 11. The real nucleotide 01 is stored in some randomly selected DDBs and the other possible nucleotide 11 is stored in remaining DDBs. In the 5th DDB, both possible nucleotides are stored. For each allele of an SNP, there is a random weight omega such that the summation of weights from all the DDBs where the real nucleotide of the allele becomes 1 and the false one becomes 0. For example, in case of real nucleotide 01 is in the first allele, we have sum of weight as 1. For the other variation 11, we have sum of weight as 0. For authentication purpose, each DDB stores another value alpha for each nucleotide of an SNP such that the summation of alpha from all n DDBs equals the summation of weights from the n-1 DDBs scaled by the authentication key mu. For example, in case of 11, sum of alpha from all the DDBs multiplied by mu is 48 and sum of weight in n-1 DDBs is also 48. Next, the query is processed in the MU for n-1 DDBs. To hide the identity of the target disease, MU includes information about other L-1 dummy diseases in the query. Let's say the target disease is X and there is only one dummy disease Y. MU then scales contribution factor beta I of the target SNPs using a constant delta and generates epsilon. For the dummy diseases, it just generates random value as epsilon. Finally, the MU concatenates all the SNPs, their risk alleles, and skill contribution factors for all the diseases into the query message. Here, this portion corresponds to the dummy disease Y, and this portion corresponds to the target disease X. MU also stores the index of the target disease information. For example, here MU stores target disease index gamma equals to 2 and the scaling constant delta. After receiving the query message from the MU, each DDB calculates total weight for each SNP. Basically, it sums up the stored weight if corresponding allele is the risk allele. For example, if risk allele is 1,1 for SNP S1, then from this table, we can see that in this DDB, allele 1 does not have 1,1, but allele 2 has 1,1. So total weight will be 0 plus 62, that means 62. Similarly, total authenticating score is calculated by adding alpha values if corresponding allele is the risk allele. From the previous example, total authenticating score will be 0 plus 2, that means 2. Next, the DDB multiplies total weight of an SNP by the corresponding contribution factor epsilon that was sent by the MU in the query message and adds up all these values to generate the partial genetic score SJK for the jth disease. Similarly, partial authenticating score is also generated for each of the diseases and returned to the MU in a return message. Next, the MU generates the query message for the nth DDB. First, it aggregates all the partial genetic scores from n-1 DDBs and generates eta JS. Next, it aggregates all the partial authenticating scores from n-1 DDBs and generates eta JM. The MU then processes the clinical values. Similar to SNP data, MU accumulates clinical values of both the target disease and the dummy diseases. Additionally, it randomly partitions clinical datasets of each disease into two separate subsets. Next, the contributions factors of the clinical data in each subset of the target disease are scaled by unique constants delta 1 bar and delta 2 bar. These partitioning and separate scaling of clinical contribution factors are done so that the nth DDB in the patient's device cannot reverse engineer value of contribution factors from the final disease risk result. For the dummy diseases, random values are generated as contribution factors. All these information are accumulated in the query message where the index of the diseases are maintained as before. Here, this portion corresponds to the dummy disease Y and this portion corresponds to the target disease X. Summation of partial genetic scores eta JS and summation of partial authenticator scores eta JM for both the target disease and the dummy diseases are also sent. After receiving the query message, the nth DDB calculates partial genetic score SJ and partial authenticating score MJ in the same way as the other n-1 DDBs. Then it checks for authentication. Basically, it adds the partial authenticating score MJ with the sum of authenticating scores sent in the query message eta JM multiplies by authentication key mu and checks if the result is equal to the sum of genetic scores sent in the query message, which is eta JS. If that's not equal, then it reports authentication error. Otherwise, it proceeds calculation. For the target disease, it generates total genetic score eta J and clinical scores eta J1 bar and eta J2 bar for each subset. Next, it changes those values by multiplying with rho and adding tau. For the dummy diseases, it just generates random values for all these scores. This is done so that a dishonest MU cannot generate a score for any disease except the target disease without patient's consent. Finally, the nth DDB sends these genetic and clinical scores for all the L diseases in a written message to the MU. MU then scales back the genetic score for the target disease eta J by multiplying with the inverse of delta. Similarly, clinical scores eta J1 bar and eta J2 bar are multiplied with the inverse of delta 1 bar and delta 2 bar constants. MU then sums up all those values and generates Z bar. It also calculates capital delta by adding inverse of all scaling constants delta, delta 1 bar and delta 2 bar. Then MU sends these values to the nth DDB. The nth DDB then reverses the effects of the multiplication and addition operations of tau and rho to generate the final disease score Z. The nth DDB also checks the relation between Z and delta to detect whether a dishonest MU have fabricated scaling constants in any way to infer SNP or clinical values. In that case, the patient can refrain from sharing the final result with the MU. We have conducted experiments to evaluate our system with and without authentication. Results show that storage size, time, and communication overhead increases linearly with increasing number of DDBs in. The authenticated system accounts for slightly more storage time and overhead. We also found that time and communication overhead increases with increased number of SNPs in a query. However, storage size is not affected. In terms of number of diseases in a query, time and communication overhead increases almost linearly with several peaks and valleys. This is because storage and overhead depends only on the number of SNPs used in a query, not on the number of diseases. And the number of SNPs related to a disease can vary in a large range. So, a smaller value of L may result in large number of SNPs in a query. We also compared our system with two cryptographic approaches by Ida et al. And Denegis et al. In the graph, our approach is shown in gray. We can see that our system performs better in terms of storage and communication overhead. In summary, we have ensured privacy of patients' genomic and clinical data, disease name, query result, and also medical unit sensitive information. We evaluated disease risk queries even when different alleles of the same SNP are responsible for different diseases, as well as authenticated the results. Besides, our approach can ensure privacy even if medical unit and databases collude. Due to time constraints, I am not explaining the proofs of privacy preserving and authentication in this presentation. Please have a look at our paper for more detailed information. Thank you for listening.